Dear children, now we can see some numericals. First question, it is well known that a raindrop falls under the influence of the downward gravitational force and the opposing resistive force. The latter is known to be proportional to the speed of the drop but is otherwise undetermined. Consider a drop of mass 1 gram falling from a height 1 kilometer. It hits the ground with a speed of 50 meter per second. What is the work done by the gravitational force and what is the work done by the unknown resistive force? So, from the question you understand that there are two forces acting on the raindrop. What are the forces? Gravitational force and the resistive force. Okay, and the resistive force is proportional to the speed of the drop. Then the mass of the drop is also given, that is 1 gram. Then change it into kilogram, that is 10 raised to minus 3 kilogram. And we assume that initially the drop is at rest, so u equal to 0. Then it moves with a speed of 50 meter per second, that is v equal to 50 meter per second. Then the height from which the drop is falling, that is 1 kilometer, then change it into meter, that is 10 raised to 3 meter. Okay, so you want to find out the work done by the gravitational force. So, there are two forces there, gravitational force and the resistive force. So, the work is done by the gravitational force and by the resistive force. So, you want to find out the Wg, that is work done by the gravitational force, and the Wr, that is the work done by the resistive force. So, according to the work energy theorem, we can write change in kinetic energy. So, you studied in the theory, that is change in kinetic energy, Kf minus Ki, that is equal to the work done. So, what is the work done here? It is due to the total work done by the gravitational force and by the resistive force. So, we can write change in kinetic energy Kf minus Ki equal to Wg plus Wr. It is the total work done. So, total work done is work done by the gravitational force plus work done by the resistive force. So, first you want to find out the change in kinetic energy. Okay, then you will find out this Wg and Wr. So, what is the change in kinetic energy? So, that we can denote it as delta K, that is equal to Kf minus Ki. Clear? So, what is the formula of Kf? That is half mv square. Then what is the formula of Ki? That is the initial kinetic energy, that is a half mu square. So, u equal to 0, so this term becomes 0. So, what is remaining here? That is a half into, what is the mass? Okay, what is the mass here? 10 raised to minus 3 kilogram. Okay, 10 raised to minus 3 into, what is the velocity? 50. Okay, so 50 into 50. Then this term becomes 0 because u equal to 0. Then when you multiply and dividing it by 2, then we will get the answer, that is 1.25 joule. So, this is the change in kinetic energy. Then we want to find out the work done by the gravitational force, that is the Wg. Okay, so this is equal to the gravitational potential energy that we studied in the next content. So, we can write mgh. So, here g is assumed to be 10 meter per second square. Clear? So, we can write mass. What is the mass here? 10 raised to minus 3 into, okay, then g equal to, that is 10 meter per second square. So, we can substitute 10 and height, that is 10 cube. So, we will get the answer, that is 10 raised to minus 3 and 10 cube will cancel. Then what is remaining? 10. Okay. So, work done by the gravitational force is 10 joule. So, if you know this change in kinetic energy and the work done by the gravitational force, you can easily find out this work done by the resistive force. Clear? So, from this formula, we can write Wr, work done by the resistive force, equal to change in kinetic energy minus work done by the gravitational force. So, we can write delta K minus Wg. So, what is the delta K here? That is 1.25. minus what is the WG, that is equal to 10. So when you subtract, you will get the final answer, that is 8.7. Okay, minus. So here 1 point minus 2, 1.25 minus 10. So we will get the answer minus 8.75 joule. So this minus sign represents that the work is done by the resistive force. Understand? So this negative sign represents that the work is done by the resistive force. So the resistive force is opposing to the motion of the raindrop. Clear? Question number 2. A cyclist comes to a skidding stop in 10 meter. During this process, the force on the cycle due to the road is 200 Newton and is directly opposed to the motion. How much work does the road do on the cycle? How much work does the cycle do on the road? Okay. So you know that work done equal to F d cos theta, where F is the force and d is the displacement and theta is the angle between the force and the displacement. So here question, a cyclist comes to a skidding stop in 10 meter. So that is the displacement of the cycle. After that it comes to the stop. So during this process, what is the force acting? That is the force on the cycle due to the road. Okay, due to the road, the force acting on the cycle is 200 Newton and the road opposes the motion of the cycle. So first question, how much work does the road do on the cycle? So here the cycle moves in the forward direction. Okay, that is the displacement of the cycle and the road opposing the motion of the cycle. That is the force of friction, isn't it? That is the stopping force, or we can say that the force of friction. So this stopping force or the frictional force and the displacement of the cycle. Okay, that is the work done on the cycle by the road is the work done by this frictional force. Okay, so the angle between these two is 180 degree. Clear? So the work done by the road, okay, the work done by the road is according to the formula, that is Fs or Fd. Okay, we can write Fd cos theta, that is equal to 200 into what is the displacement of the cycle, that is the 10. Then what is the angle between the displacement and the frictional force by the road on the cycle, that is equal to 180 degree. So we can write cos 180 degree. Clear? So that is cos 180, that is the minus 1. So we will get the answer minus 2000 joule. So the negative sign represents that the work, that is the work done by the frictional force on the cycle. So that is work is done by the road on the cycle and it is the opposing force. It is the frictional force that is represented by this negative sign. And what is this is the first part. And what is the second part? Okay, second part, how much work does the cycle do on the road? When the first case, the road exert a force on the cycle, that is the 200 Newton. And here, the how much work does the road do on the, that is second question, how much work does the cycle do on the road? Okay, so if the cycle exert a force, is there any displacement of the road? There is no displacement, isn't it? So what happens here? What is this formula will become? This formula, that is the displacement is 0, isn't it? So here also the force is 200 Newton because according to the Newton's third law, an equal and opposite force act on the road due to the cycle. So the force, the magnitude of the force is 200 Newton, but there is no displacement. Okay, there is no displacement of the road. So we can write work done by the cycle, okay, work done by the cycle on the road, that is equal to 0. Clear? So this is the second part. Clear? Third question. A woman pushes a trunk on railway platform which has a rough surface. She supplies a force of 100 Newton over a distance of 10 meter. Thereafter she gets progressively tired and her applied force reduces linearly with distance to 50 Newton. The total distance by which the trunk has been moved is 20 meter. Plot the force applied by the woman and the frictional force, which is 50 Newton. Calculate the work done by the two forces over 20 meter. Okay. So, in this question, first you want to draw a force displacement graph. That is the plot the force applied by the woman and the frictional force, which is 50 Newton. So, for this you want to draw the force displacement graph. So, here a woman pushes a trunk on railway platform which has a rough surface. So, what is the force applied by the woman? That is 100 Newton. So, up to a distance of 10 meter. Then after that what happened? She progressively tired and then his force reduces to 50 Newton. So, the total distance travelled by the trunk has been moved is 20 meter. Then you want to draw the graph. So, we can draw the force displacement graph. So, we should take the force along the y-axis. Okay, force along the y-axis and the displacement along the x-axis. Okay, so we can note it as force in Newton and the displacement, that is in meter. Okay, and this is the origin. And here the opposing force is there, frictional force is there. So you want to draw the negative axis, force also negative axis. Okay, this is, we can note it as minus F. Then what are the force? So here first that is when she progressively tired, his force reduces to 50 Newton and the first she supplies 100 Newton force, etc. So we can plot here, that is 50 Newton. Okay, 50 and 100. Then the distance we can note, that is the 10 meter. Okay, 10 meter and the 20 meter. Clear? Now we can plot the graph. So what is the first case? She supplies a force of 100 Newton over a distance of 10 meter. So how can you draw here? She supplies a force of 100 Newton over a distance of 10 meter. Clear? So we can draw like this, isn't it? Okay. 100 Newton and over a distance of 10 meter. Then what happens? Then thereafter she get progressively tired and her applied force reduces linearly with a distance to 50 Newton. Okay, so he progressively tired and his force reduces linearly to a distance of 50 Newton. Okay, his force reduces to 50 Newton, but the total distance travelled by the trunk is 20 meter. So here his force reduces to 50 Newton and but he travel a distance of 20 meter. The trunk travel a distance of 20 meter. So we can plot the graph like this. Okay, here we can use it dotted lines, isn't it? So this is the graphical representation. So once again, here she progressively, that is here, that is the 50 Newton. Okay, this is the 50 Newton and then total distance travelled by the trunk is 20 meter. So first she applies a force of 100 Newton and the trunk travel a distance of 10 meter. Then she progressively tired and his force reduces to 50 Newton, but the trunk travel a distance of 20 meter. Clear? Then what happened? The total distance. Then the second one, the frictional force. Okay, plot the force applied by the woman and the frictional force which is 50 Newton. Okay, then 50 Newton force, frictional force also you want to note here. So here we can note it as that is the minus 50. Okay, so this is the frictional force. Frictional force is from the starting point to the 20 meter. Okay, starting point to the 20 meter, that is the frictional force is there. Okay, up to this frictional force is here. Then what do you want to find out here? So you want to find out the work done by the two forces over 20 meter. So what are the two forces? Work done by the applied force by the woman. Okay, work done by the force applied by the woman and work done by the frictional force. These two work done you want to calculate. So we can write, first we can write work done. Okay, work done by the force applied by the woman. Okay, so here the forces are variable. How it is variable? First the 100 Newton force, second then 50 Newton force, etc. Okay, so the force is variable. So when the force is variable, how can you find out the work done? It is equal to the area under the graph. Clear? It is equal to the area under the graph. So we can write here work done by the applied force, that is WF equal to, what is the area under the graph? The area is in the shape of a rectangle. Okay, area is in the shape of a rectangle and it is in the shape of a trapezium also. Two areas are there. So this is the work done by the applied force. So first 100 Newton force, then 50 Newton force. Okay, so the total area is under the graph. The total area under the graph is this one. So that area is in the shape of a rectangle and it is in the shape of a trapezium. Okay, so we can write work done by the applied force equal to area of rectangle. Okay, area of rectangle plus area of trapezium. So what is the area of rectangle from the figure? So that is equal to, this is 100. Okay, length, and this is the breadth. Okay, 100 into 10. Okay, so we can write 100 into 10 plus what is the area of trapezium? That is half into sum of the parallel side. What is the parallel side? These two are the parallel sides. Clear? So what is this distance? 100. And what is this distance? That is the 50. Okay, so half into, okay, half into 100 plus 50. Then what is the height? What is the height here? That is, this is the height. Okay, height of the trapezium. 20 minus 10 into 10. Okay, so that is, so when you multiply and adding and multiplying, you will get the answer, that is 1750 joule. This is the work done by the applied force. It is equal to the area under the graph. Then what is the second one? Work done by the frictional force. Clear? Work done by the frictional force. It is also equal to the area under the graph. Clear? So what is the area under the graph? It is in the shape of a rectangle. Okay, so what is the area here? 50 minus 50 into 20. Clear? So we can write minus 50 into 20. So that is equal to minus 1000. Okay, 1000 joule. So this minus sign represents that work done by the frictional force. Clear? Minus sign represents that work done by the frictional force. So if there is a variable force, you can find out the work done. It is equal to the area under the graph. Then fourth question. In a ballistic demonstration, a police officer fires a bullet of mass 50 gram with a speed 200 meter per second on soft plywood of thickness 2 centimeter. The bullet emerges with only 10% of its initial kinetic energy. What is the emergent speed of the bullet? So mass of the bullet is given, that is a 50 gram. Change it into kilogram, that is 0.05 kilogram. Then what is the speed of the bullet? Initial speed of the bullet, that is equal to 200 meter per second. Okay. Then it is given the bullet emerges with only 10% of its initial kinetic energy. That means its final kinetic energy is equal to the 10% of initial kinetic energy. So first we want to find out the initial kinetic energy. Then we can find out the emergent speed of the bullet. Okay, so initial kinetic energy. Okay, initial kinetic energy equal to half mu square. So that is equal to half into 0.05 into, what is the initial velocity? 200 meter square. Okay, 200 meter per second. That is equal to 200 square, isn't it? So after calculating this one, we get 1000 joule. Clear? 1000 joule. Then if you want to find out the emergent speed of the bullet, so for that you want to find out the final kinetic energy. So we can write final kinetic energy, okay, equal to, what is the final kinetic energy? 10% of initial kinetic energy. What is the initial kinetic energy? 1000. Clear? So that is equal to 10 into, okay, 1000 divided by 10%, that is 10 by 100 into 1000, that is equal to 100 joule. Clear? This is the final kinetic energy. So we can find out the emergent speed. What is the final kinetic energy formula? Half mv square equal to 100 joule. So from this we can find out the V. So V equal to, okay, V equal to 100 into 2, okay, divided by mass. What is the mass here? That is equal to 0.05. And here it is V square, so we can put root of. So the answer becomes 63.2 meter per second. So this is the emergent speed of the bullet. Okay, clear?